we're gonna continue talking about measures of central tendency, and it's important to understand the relationship between the mean and the median. All right, and the best way to show you that is to do an example. And I've started out by writing an example for us. So go ahead and pause your video and write this problem out. I'll give you a second. So the duration of your last 12 phone calls are given in table 1. Find the mean and the median. So let's just start out by doing that, and then we'll do some comparing here. So the mean we'll label as mu. That's equal to the sum of all the phone calls divided by the total number of phone calls. So 1 plus 7 plus 4. Just going to write them all out here. All right, and that's divided by 12, the total number of calls. So you do the math there and you get 7.25 minutes. And be sure to label things so we know, and I know, and your audience knows what you're talking about. It's 7.25 minutes. That is your mean call time. All right, now let's find M, the median. How do you find M, the median? Well, you have to arrange everything in ascending order. So you get 1, I'll write median here so your notes look a little better. 1, 1, 2, 3, 3, 3, 4, 4, 5, 6, 7, and 48. So to do this, I'll just start from the outside, counting in 1, 2, 3, 4, 5, 5. So I found that these two are in the middle. So to find the median, M, I take these two and find the average, which will give me 3.5. So now I found M to be 3.5 and my mean to be 7.25. So my next question here is an important one, and the reason for this example. Example 2, which measure of central tendency best describes the length of a typical phone call? All right, this is where the relationship between the mean and the median are going to come into play. And off the bat, you may not be able to tell right off the bat. So the easiest way to do that is we can draw a dot plot, meaning we just draw a line here, and we'll start at 0. And since we go out my lowest value is 1, and it goes out to 48, which is quite big. So what I'm going to do is I'm just going to go by 7, 7, 14, 21, 28, 35, 42, and 48. 49. Man, I'm off today. 21, 28, 35, and 42. All right, so I just went incrementally by sevens. And now I'm going to draw dots everywhere a phone call occurred. So I'm going to go based off of this ascending order that I just wrote here. So I have 2 at 1, so just 2 dots here, and then 1 at 2, and then 3 at 3, 1, 2, 3, 2 at 4, 1 at 5, 1 at 6, 1 at 7, and then 1 at 48. Sorry, it's a little small. Should have drew bigger dots. So now that we have our dot plot finished, let's now add our mean and our median. So the mean is 7.25, which is, let's just say right here for argument's sake, that's our mean. And then our median is 3.5. So 1, 2, 3.5, which is here. So now looking at this graph, can you tell me which measure of central tendency, meaning the mean or the median, is a better describer or more accurately describes my average phone call? The median does, because it lies closer or in center of the bulk of the data, whereas the mean is pushed way out here, and there's 11 phone calls on this side of the mean and only 1 out here. The reason is because the mean is affected by very large values. So this value of 48 is affecting the mean. If I were to change this 48-minute phone call to say 148 minutes, then that would change the mean all the way to 15 minutes. But it would leave the median in its exact spot. So the further and further this phone call or this outlier gets pushed further out, the mean's going to chase it, but the median will stay put. So let's talk about what that means about the mean being affected by extreme values. So we have, let's do a star here. This will be important to know. The mean is affected by extreme values and the median is not. So the median is said to be resistant. And we're going to define exactly what resistant means also, because that is a definition. It's important to know this. The mean is affected by extreme values, and the median is not. The median is resistant. Resistant means, let's do another star for resistant. That definition is extreme values very large or small, and it has to be relative to the data. So extreme values relative to the data do not affect its value substantially. And as you saw in our previous example, it doesn't matter about this 49 or this 48 out here. The median will not change. Even if this 48 was sent to 100 minutes or 500 minutes, the median would stay the same, but the mean would chase it. It would continue getting larger. All right, so this leads to some important graphical representations of what we're talking about. And so the first one is, let's say it's bell-shaped, which we've talked about bell-shaped in a previous video, and it will look very similar to what we've seen. Bell-shaped, it's also symmetric. And this is the ideal case. So you could have, say this is your chart here, and this, I'll try to make this as bell-shaped as possible. Where it's even, symmetric on both sides. That is bell-shaped. When you have something bell-shaped, that means the mean, this means the mean, mu, is equal to the median, m, and this is the value of both of them, the same value. This graph is the mean equals the median. So when we have a bell-shaped graph, that means the mean and median are the same thing, and we have a pretty good representation of what's going on. The other two that we can have are something that we've seen before already. Skewed right. So here's our graph of something skewed right. Remember, skewed right means the bulk of the data is on the left. So skewed right means there's a bunch of little tiny outliers out here that's skewing all of our data this way. So we would have something like this. The smaller outliers are to the right. That's why it's called skewed right. Our bulk of our data lies here. So when we have something like this, our median will lie somewhere right here. Median. Whereas our mean will be somewhere right here. And this is the same example that we have in example 2 or example 1, whichever you want to call it. If you look at our dot plot here, most of our data is here on the left, and we have outlier data to the right. So what that's doing is it's leaving our median here, but it's pushing our mean out this way. And that's the same thing we have here. Our median is here, but these outliers, this skewed right graph, is pushing our mean outwards. So this is the situation where the mean is greater than the median. And the last option is skewed left. We have some data that's really small over here, but most of our data is over here on this side. So here, this would mean that our median is here, roughly, and all of these data points are forcing our mean to the left. And this is the case where our mean is less than the median. So it's important to understand this relationship with the mean and the median. And the most ideal case is when we have our bell shape, when the mean and the median are same or very close to the same. So take a look over this, understand that the median is not resistant. The median is resistant. It's not affected by extreme values. All right? That's it for now.